There are systems in engineering that help you operate better, systems that help you monitor better, systems that help you optimize better. And then there are systems that exist because one failure cannot be allowed to become a disaster. HIPPS belongs to that last category. A high-integrity pressure protection system is not just another shutdown system, not just another instrumentation package, not just a logic solver with a high SEAL certificate, not just a fast valve, not just another vendor skid that project teams push through engineering, procurement, FAT, SAT, T, and commissioning. HIPPS is the last engineered barrier between a credible overpressure event and a downstream system that was never designed to survive that pressure. That is where engineering becomes brutally honest. Because when normal control fails, when pressure regulation fails, when a control valve sticks open, when a transmitter lies, when a bypass is wrongly lined up, when operations is under pressure, when maintenance has left one hidden weakness behind, HIPPS is the system that must still act. No excuses, no delay, no dependency on operator heroics, no waiting for SCADA graphics to refresh, no hoping that the plant will settle down by itself. It must detect, decide, trip, vent, close, isolate, and hold the safe state. That is the raw truth. If you are a design engineer, trainee engineer, instrumentation engineer, process engineer, mechanical engineer, safety engineer, commissioning engineer, or project engineer, you need to understand this deeply. HIPPS is not designed from a block diagram. HIPPS is designed from a hazard. The first question is not, which vendor are we using? The first question is, what must not happen? The downstream system must not be exposed to pressure beyond its safe design envelope. That sounds simple, but behind that one sentence lives the full engineering discipline. What is the maximum credible upstream pressure? What is the downstream design pressure? What is the pressure rise rate? What is the trip set point? What is the allowable response time? What failure has created the demand? What equipment is being protected? What proof do you have that the final valve will close fast enough? What happens if one transmitter is isolated? What happens if one output short circuits? What happens if the solenoid sticks? What happens if the actuator has lost torque after sitting open for a year? What happens if the reset is too easy? This is where weak engineering gets exposed. A poor engineer asks, is it SIL certified? A strong engineer asks, will the complete safety function work when the plant is already in trouble? That is the difference. HIPPS is a personality test for engineering teams. It reveals whether your project culture is serious or cosmetic. It reveals whether your discipline interface is real or just meeting minutes. It reveals whether your design reviews are technical or ceremonial. It reveals whether your FAT is a proof test or a photo opportunity. It reveals whether your SAT is acceptance testing or schedule theater. It reveals whether your engineering team understands consequence, and consequence is the real teacher here. In normal operation, pressure control keeps the plant stable, but control is not protection. Control is designed to regulate. Protection is designed to stop escalation. If you confuse the two, you have already started building a dangerous plant. The pressure control valve may normally reduce pressure beautifully, but if it fails open, the downstream system sees a pressure it may never have been designed to contain. The HIPPS must step in. It uses pressure transmitters to detect high pressure. It uses voting logic to avoid being fooled by one bad signal. It uses a fail-safe logic solver to decide when the trip condition is real. It de-energizes outputs. It drives solenoids into the safe action. It vents actuator pressure or shifts the control circuit. It releases spring energy. It closes the final isolation valves, and then it prevents automatic reset. That last part matters more than many young engineers realize. After a HIPPS trip, the system must not reopen just because the pressure has dropped. That would be insane. Pressure rises, HIPPS trips, valve closes, pressure drops, valve reopens, pressure rises again, and now your so-called protection system has become a dangerous cycling machine. Manual reset forces the human being back into the loop at the correct point, not to save the plant during the dangerous moment. The system already did that. The human returns after the trip to assess, diagnose, confirm, and deliberately restore. That is mature safety philosophy. You do not design reset for convenience. You design reset for accountability. Now let us go deeper. The most misunderstood part of HIPPS is not the logic solver. It is the final element. Most people love talking about SIL, voting logic, certified modules, diagnostics, and safety calculations. But the shutdown valve and actuator are where engineering meets reality. That valve may sit open for months, maybe for a year. Then suddenly it must close fully in less than a few seconds under high differential pressure. Think about what you are asking from that piece of equipment. The seat may have aged. The seals may have changed. The breakaway torque may have increased. The spring may have relaxed. The actuator may be working at minimum gas supply pressure. The tubing may restrict venting. The solenoid may be slow. The quick exhaust valve may not behave as assumed. The coupling may be under-designed. The valve stem may face higher torque than allowed. The speed control may be misadjusted. The valve may move, but not fast enough. Or worse, it may receive the close command and not actually close. This is why command is not reality. A closed signal is not a closed valve. A de-energized output is not isolation. A solenoid click is not protection. A partial movement is not the safety function. The real proof is full closure within required response time. That means full loop testing matters. You must test the transmitters, the voting, the logic solver, the outputs, the solenoids, the actuator, the valve, the position feedback, the alarms, and the reset philosophy as one safety function. Not separately, not symbolically, not with assumptions, as a loop. This is why FAT can make or break the future of a HIPPS package. A weak FAT tests signals. A strong FAT tests consequence. A weak FAT checks if the panel lights come on. A strong FAT checks if the system trips correctly. A weak FAT validates documents. A strong FAT challenges assumptions. A weak FAT is vendor-friendly. A strong FAT is plant-friendly. And that is the standard you should hold. Now look at the sensing side. HIPPS typically uses 3 pressure transmitters with 2 out of 3 voting. On paper, this looks beautiful. One transmitter can fail and the system still protects. One transmitter can give a false trip and the plant does not unnecessarily shut down. But voting only works when common cause failure is controlled. 3 transmitters are not truly independent if the same process tapping can be blocked. They are not truly independent if the same manifold can isolate all of them. They are not truly independent if maintenance can accidentally remove the sensing function without alarm. They are not truly independent if all 3 are misranged, misconfigured, or exposed to the same hidden installation weakness. That is why the high-integrity manifold block matters. It is not a small piping accessory. It is a human error barrier. It should prevent unsafe isolation. It should alarm when a transmitter is isolated. It should allow maintenance without silently defeating the system. That is real design thinking. You are not only designing equipment, you are designing against human error because people will make mistakes. Maintenance will happen, testing will happen. Pressure transmitters will be isolated, solenoids will be checked, valves will be stroked, panels will be opened, cables will be terminated, alarms will be acknowledged. And if your design depends on perfect human behavior, your design is weak. A good HIPPS design makes the safe action natural and the dangerous action difficult. Now think about the logic solver. The logic solver is the brain, but it must not become an ego center. It must be dedicated, fail-safe, fault-tolerant, diagnosable, and independent. It must distribute critical inputs across cards. It must monitor open circuits, short circuits, and ground faults. It must ensure one output fault does not take down other outputs. It must provide clear local indication. It must send meaningful alarms. It must not depend on SCADA to perform the protective action. SCADA is visibility. HIPPS is protection. Do not confuse the display with the decision. The trip must happen even if the operator screen is dead. The trip must happen even if communications fail. The trip must happen even if nobody is watching. That is the entire point. This is also why cabinet engineering is not minor. Young engineers sometimes treat panel details as low-level drafting work. Wrong. Cabinet design can silently destroy reliability. Poor earthing creates noise problems. Poor segregation creates interference. Overfilled ducts make maintenance ugly. Bad labeling creates troubleshooting mistakes. Weak thermal management accelerates failure. Poor gland plate design creates installation problems. No spare space creates modification risk. Bad fuse coordination creates nuisance failures. No clear, clean earth and dirty earth philosophy creates signal quality issues. A safety cabinet is not just a box. It is the physical home of the protection brain. If you make it messy, hot, noisy, corrosive, cramped, or poorly documented, you are degrading the safety function before the first trip ever happens. And let us be honest about SIL. SIL is one of the most misused words in project engineering. A SIL certified component does not make a SIL compliant function. A certified logic solver does not save an undersized actuator. A SIL-rated transmitter does not save a bad manifold. A certified solenoid does not save poor tubing. A beautiful calculation does not save a poor proof test. A third-party certificate does not save bad installation. SCL is not a sticker. CL is a life cycle. It must survive design, procurement, integration, FAT, shipment, installation, SAT, commissioning, operation, maintenance, proof testing, modification, and eventual replacement. That is the mature view. The immature view is to collect certificates and call the system safe. Now let's talk about the hidden emotional reality of engineering. Nobody wants to admit their design is fragile. Nobody wants to delay procurement. Nobody wants to reject a vendor calculation late in the schedule. Nobody wants to tell management that the FAT is inadequate. Nobody wants to reopen the reset philosophy. Nobody wants to challenge the final element sizing when the delivery date is already tight. Nobody wants to be the person who slows the project. But safety engineering demands backbone. If the actuator torque data is incomplete, you challenge it. If the stroke time is assumed, you demand proof. If the manifold can defeat sensing, you redesign. If the reset is unsafe, you correct it. If the FAT is shallow, you expand it. If the SAT is being rushed, you raise the issue. If documentation is generic, you reject it. This is not negativity. This is engineering integrity. The plant does not care about your schedule pressure. Pressure does not care about your procurement milestone. A failed valve does not care about your meeting minutes. A hidden fault does not care about your dashboard. Physics will collect the truth. Always. That is why HIPPS teaches discipline. It teaches you to respect consequence before consequence teaches you violently. Now think about careers. The engineers who master systems like HIPPS become different. They stop thinking like component selectors. They start thinking like risk owners. They become stronger in design reviews because they understand interfaces. They become stronger in vendor meetings because they know what evidence matters. They become stronger in commissioning because they know what must be proven. They become stronger leaders because they can separate paperwork confidence from technical confidence. This kind of engineer is valuable because industry does not need more people who can repeat standards. Industry needs people who can interpret risk, challenge assumptions, and protect the plant. That is the career growth hidden inside HIPPS engineering. It trains your mind to see systems. It trains your judgment to see weak links. It trains your communication to ask harder questions without drama. It trains your leadership to defend technical truth under schedule pressure. It trains your discipline to distinguish compliance from capability. And that same mindset affects your personality as an engineer. You become less impressed by labels. You become less seduced by vendor language. You become less dependent on authority. You become more evidence-driven, more precise, more grounded, more difficult to fool. You begin to understand that engineering maturity is not about sounding intelligent. It is about preventing failure before anyone outside the project realizes failure was possible. That is the standard. Now bring this into real project situations. In design, HIPPS forces process, instrumentation, mechanical, piping, electrical, safety, automation, QA/QC, construction, commissioning, operations, and maintenance teams to align. If one discipline works in isolation, the package becomes dangerous. Process defines the overpressure scenario. Instrumentation defines sensing and logic. Mechanical reviews valve and actuator integrity. Piping confirms layout, ratings, and access. Electrical protects power and earthing. Automation manages interface and alarms. Safety validates the life cycle. QA/QC verifies materials, inspection, and testing. Commissioning proves the installed function. Operations owns reset and response. Maintenance preserves proof testing. HIPPS is not a discipline package. It is a cross-discipline truth test. If the interfaces are weak, the system is weak. If the ownership is unclear, the system is weak. If the testing is fragmented, the system is weak. If the documentation is not as built, the system is weak. This is why engineering management matters. Good engineering managers do not treat HIPPS as procurement scope. They treat it as a safety-critical integration package. They force early clarity. They demand an approved functional design specification. They insist on third-party verification. They protect FAT quality. They ensure SAT-T is meaningful. They make sure operations and maintenance understand the system before handover. They do not allow safety to become a paperwork ritual. Now let us cut through the comfortable myth. Most failures are not dramatic at the beginning. They begin quietly. A slightly vague requirement, a generic data sheet, a missing torque calculation, a test procedure that avoids the hard scenario, a punch item carried forward, a cabinet drawing not updated, a transmitter alarm not mapped, a reset sequence not understood, a maintenance manual copied from a catalog, a proof test interval nobody owns, a commissioning spare consumed but never replaced. One weakness becomes two become five become a hidden condition. Then one day the plant demands the system, and the system gives back the quality of the engineering that created it. That is raw. That is uncomfortable. That is true. So if you are listening as a trainee engineer, remember this. Do not worship drawings. Interrogate them. Trace the safety function. Ask what happens when pressure rises. Ask what happens when one transmitter is wrong. Ask what happens when a solenoid fails. Ask what happens when the actuator supply is lost. Ask what happens when the valve does not confirm closed. Ask what happens after trip. Ask who resets. Ask how proof testing is done. Ask what the operator sees. Ask what maintenance can accidentally defeat. Ask what evidence proves the system. That is how you become an engineer, not by memorizing standards, by understanding failure. And if you are an experienced engineer, be honest. Where have you seen this go wrong? A valve that did not stroke within time. A solenoid bypass left in the wrong state. A transmitter isolated without clear alarm. A FAT that passed too easily. A SAT that became a formality. A SIL calculation that ignored real maintenance behavior. A final element that dominated the failure probability but received the least attention. These are not just technical stories. They are lessons written in risk. The value of HIPPS engineering is that it disciplines the mind. It tells you that protection is not a claim. Protection is a demonstrated capability. It tells you that certification is not enough. Testing must prove the function. It tells you that control is not protection. Independence matters. It tells you that reset is not convenience. Reset is accountability. It tells you that the final element is not hardware. It is the physical execution of the safety decision. It tells you that engineering is not about looking correct. It is about being correct when the system is under demand. That is the real message. HIPPS is quiet most of the time. It does not ask for attention. It does not produce daily excitement. It sits in the background while production continues. But when the wrong pressure arrives, when normal control fails, when downstream equipment is exposed, when seconds matter, HIPPS must become absolute. Detect, vote, trip, isolate, hold, no drama, no negotiation, no excuses. That is engineering at its cleanest. That is protection by design. That's why you study HIPPS seriously. And that is why, if you want to grow as a design engineer, safety engineer, instrumentation engineer, project engineer, commissioning engineer, or maintenance professional, you need to go beyond the surface. Do not just learn what HIPPS is. Learn how it fails. Learn how it is proven. Learn how it is misapplied. Learn how it is maintained. Learn how it protects the plant when everything else has already gone wrong. Because the real question is never, does the package look compliant? The real question is, will it close fast enough when the plant has lost normal control? If that question makes you uncomfortable, good. That discomfort is the beginning of engineering maturity. If this kind of deep engineering breakdown speaks to you, stay connected. Like, share, subscribe, and follow for more engineering white papers, tutorials, design lessons, failure mode breakdowns, commissioning insights, and practical project engineering discussions. And if you want a deeper technical reading, a focused engineering review, or a guidance session that works for your specific learning path, project role, discipline, or career direction, get in touch with me for a reading, one that works for you. Because real engineering growth does not come from collecting information. It comes from learning how to see what can fail before it fails.